All right, let's work through problem 58 on page 8, which is associated with the assigned problem 55. And both of these problems are compound problems in the sense that they make use of both the distance and the midpoint formula. In the case of 58, it says verify that the points, and it gives 3 points, are vertices of an equilateral triangle. So we're going to have to set up a picture here and then use the distance formula to show that the various sides are all the same. It then goes on and says that then show that the midpoints of the 3 sides are the vertices of a second equilateral triangle. So I'm going to do this in a kind of a shortcut type manner. I'm just going to set up a Cartesian plane here, and the points that are given, I'm going to call the first one A. It is the origin, point 0, 0. The second one is the point A0, and I'm going to call that point B. And then the third one is midway between and a little bit up. I'm going to draw it right there, kind of anticipating the outcome. And it's the point A over 2, root 3 over 2 times A. Okay? So, indeed, there is a little triangle here. I'm going to dot all of these. And let's just quickly, without doing everything, you really have to show that this side is equal to that side and that this side is equal to that side. Let's just do a shortcut here, and let's show that this side right here, which is segment AB, has the same length as this side, which is segment BC. So if I just use the distance formula here in this case for A and B, I take the difference between the two A values, A minus 0, and I square it. I take the difference between the two Y values, 0 and 0, and square it. And then I take the square root of all of that. Okay? And very quickly you can see that this is A squared plus 0. Take the square root of A squared. You get A. Okay? And we knew that at the outset. The length of this segment is just A. It's the distance from the origin to the point A. And now let's go look at this, this distance right here. That is the length of segment BC. Again, using the distance formula, I just have to subtract the two x coordinates, and I'll leave it to you whether you want to subtract A over 2 from A or A from A over 2. Once you square it, you really don't care which way you affect that subtraction. And likewise, I'm going to subtract the two y coordinates now, 0 in this case, and root 3a over 2 in that case. Square them, take the square root, and what you're going to be left with on the interior is a minus a over 2 is a over 2 squared. I'm going to write that a squared over 4. And 0 minus root 3 over 2a squared is going to be 3 over 4a squared. I'm going to have to take the square root. And sure enough, I've got 1/4 a squared and 3/4 a squared. I'm pretty sure that's a squared. And if I take the square root, I see that the length of side BC is indeed the same as the length there. And if we were to go ahead and find the length of AC, I'll leave that to you to do. You'll find that its length is A as well too. So that's the first part of the problem. The second part says, let's go find these midpoints. All right. And let's show that this triangle is also a equilateral triangle. So, gosh, a little bit more work, but let's see if we can make short work of it. This midpoint has got an x coordinate and a y coordinate. And remember, those coordinates are the average of the corresponding x and y coordinates on either side on the endpoints. So to find the x coordinate of this value, I just add this value to this value. I get a, let's do it explicitly, a over 2 plus a all over 2. and I get root 3a all over 2 plus 0 all over 2. I'm going to bring that down here. That is the point. That is the point 3a all over 4 and root 3a all over 4. Okay. And likewise, this point, this one's a little easier to do. This is the point a over 2, 0. I'm going to have to label all of these again. I'll do that in just a moment. And to find this point, I've got to take this value, add it to this value, a over 4 divided by 2. Take this value, add it to this value, divide by 2, root 3a over 4. So there's my 3 points. I'm going to have to call this D, E, and F. Okay. And let's do the same thing that we did here. Let's find, first of all, the length of segment DE. All right, what is this length? This should be fairly easy because these 2 points have the same y-coordinate. Sure enough, it's root 3a over 4. And so this distance should be just the difference in their x-coordinates. One is 3a over 4, the other is a over 4. That should leave 3a over 4 minus a over 4 is 2a over 4, or a over 2. So this length is a over 2. What's left to us is to show that these 2 lengths are also a over 2. And again, I'm just going to do one of the 2. I'm going to go and find the length of this segment DF. Here are the coordinates of D and F. I'm going to use the distance formula again. Let's go find the difference in the x-coordinates. Add to that the difference in the y-coordinates. Square these guys and take the square root. So it's a little arithmetic left to do. A over 2 minus a over 4 is a over 4 squared is a squared all over 16. 0 minus root 3 a over 4 is root 3 over 4. Let's square that and get 3a squared all over 16. Take the square root. I've got 1/16 a squared. I've got 3/16 a squared. That's 4/16 a squared. Take the square root. And sure enough, 4 over 16 is 1/4. Take the square root of a squared over 1/4 and you get a over 2. And indeed, the length of segment DF is the same as the length of segment DE. I would leave it to you to show that EF, the length of this segment, is indeed a over 2 as well too. So there you go, multiple applications of the distance formula and the midpoint formula to work out this problem.